energy is equal to your work plus your heat. Okay. And it says a system gains 657 kilojoules of heat. So it gains 657 kilojoules. Work equals energy. And it says the energy change was, yeah, those keys don't work. I can't get any of the keys to work. I couldn't get one to hear it. Yeah. Okay. Energy is equal to 186 equals work plus 657. So W equals 186 minus 657, which is negative 471. So I think that's all it is the minus sign. Does that make sense? Okay, perfect. That should fix that one. Hi, Cassandra. We're just going to some of the questions here Tara has. I got your question. I got your email. I'll get your text too. So I'll go over those also, okay?
Oh, you got my text?
Got you. Yeah.
Oh, okay. I was like, oh no, did I log on too late? He's already going over mine.
No, we just go to one of the questions you had real quick. No, you're fine. No problem. Like I said, I'm still up in Utah. So it's 7 o'clock here. It's an hour ahead of California. So let's do that.
We got the dog.
You got the dog? Hey, pumps. All right. And there's another one I want to go over quick too here.
We had a race to the door.
All right. Was the heated solution we did last time was water and potassium hydroxide. And where it says it's massive solution. Okay. So they have the mass of the water, the mass of potassium hydroxide, the temperature. You want to give him some extra water?
Oh, yeah, of course.
He's not even finish it all. It says the temperature change was 17.55 after the addition. So it says then calculate gain, heat gain heat gain or loss by the solution and give the specific heat of water. So you got to see the assumption you have to make. It's not a good question. The assumption you have to make is the specific heat of water is also the specific heat of the solution. That's not going to change much just by adding 5 grams of water, 5 grams of potassium hydroxide to the 7 grams of water. That's an assumption they didn't say to make, but you have to make that to do the problem. And you know the equation, specific heat. Or I'm sorry, not specific heat. Q equals specific heat mass delta T. That gives you the heat gained or heat lost by the system. Okay, so the specific heat, we're going to make the assumption the specific heat of the solution is the same as the specific heat of water, which is 4.184 joules per gram degrees centigrade. The mass of the solution is 70 grams of water and 5 grams of potassium hydroxide. So the total mass of the solution is 75 grams. Right? And the delta T is a change in temperature. You for that 17.55. Okay, so Q is your energy or heat exchange from the system. Okay, and you can say 4.184 times 75 times 17.55. And get my calculator here. I can't do that one in my head. Although Susie probably could, right? 4.184 times 75 times 17.55 equals 5,507 joules. Okay, so 5,507.19 joules. And they want the answer in kilojoules, right? Convert that to kilojoules, remove the decimal point in 3 places. Because you remember, if we had joules, and the conversion would be kilojoules K means 10 to the third because it's 1,000. Okay. And you bring it up, you change the sign. So you move the decimal point 3 places to the left. 1, 2, 3. So it should be 5.51 because 0 rounds off to 1 because it's 7 kilojoules. Right? 1, 2, 3 sections. Yep, 5.51 kilojoules. Right? Does that make sense now, Tara? I think that's what that's the assumption you got to make. Like I said, it's not a good question. I wouldn't ask a question that way because you have to make an assumption and they don't tell you. It's, yeah, I didn't like it either. And the molar heat, we just use that same number. It's all right. Cool. All right. Like I said, we got lots of questions today. You want to do chapter 9, then we'll start answering all the questions. All right. Does that sound good? Go through
Okay.
chapter. Okay. Is there any burning questions before you want to start chapter 9? No burning questions? Okay. So let's go to chapter 9. I think I got it pulled up here, actually. All right. Chapter 9 is on covalent bonds, octet rule, which you talked about before. And we're getting something, it's a little different called formal charge. It's kind of funny at first, kind of like the electron configuration that we did, but it'll make sense in a little while. So when we do covalent bonds, everything has, we want the octet rule. We want everything to have 8 to become stable. And we know we're going to use valence electrons. Valence electrons are the electrons around the element. And that is strictly off the periodic table. So if we go to our periodic table, okay, these are our rows, right? This row is number 1. This row is number 2. Okay, this is your transitional metals. They have different valence electrons. This is 3. This is 4, 5, 6, 7, and 8. Just like the number, there's it's a letter on your periodic table. It says 1, 2, 3A, 4A, 5A. Those are your elements. The transition ones vary. So if you look at the periodic table, look at aluminum. Aluminum is in what row? 3A. It has 3 valence electrons. Okay. If you look at sodium, sodium's in column 1, 1A. It has 1 valence electron. We're going to need that when we do our Lewis structures and when we do our electrons. So all the valence electrons are determined by the periodic table, just plain and simple. Look at silicon. Silicon has how many valence electrons? Silicon's right here.
So it'd be 4.
Perfect. It has 4. What does bromine have?
7.
Yeah, that's exactly how you do it. Okay, so you should know valence electrons. You know for every element now. Just look at the periodic table. It's right there. And these noble gases, these are your noble gases here. Those all have 8 valence electrons, which means they are stable. That's why they're called noble gases. They don't react with anybody. Noble, they're snooty. They don't associate with the lower class elements. Okay, that's what they're called noble gases. They don't even react with themselves. Okay? All the other gases are diatomic, like oxygen is O2 that we did, nitrogen's N2, argon is just AR, helium is just HE. You know, they don't interact with each other. They have 8 valence electrons and they're happy. They're stable. Okay, so the octet rule means everything wants to have 8 valence electrons. Okay, so if we go to, let's actually, Izzy showed me how to do this. There we go. We can clear that. Okay, so if we're looking at sharing a bond, covalent bonds, we're going to share bonds so they end up with 8 valence electrons. Let's take chlorine for an example. Chlorine has how many valence electrons? 7, right? Everybody know what chlorine has 7 valence electrons? It's in column 7A. Okay, so yeah, another chlorine here. Let's do a second one. And it has 7 valence electrons. Okay, notice it can share 2 electrons between them. That's why chlorine gas is diatomic. It is Cl2. Because now each one, and we would write this like this. Okay, Each one has 8 valence electrons around it. Because remember, when we draw a line, that's a chemical bond. Every chemical bond has 2 electrons in it. So every single line we draw has 2 valence electrons. Okay? And you want to make everything have 8. And it's happy. So you can see why chlorine is stabilized. Each one of these has 8 valence electrons around it. There's 2 in that little bond because they share it. Okay? Each one has 8 and they're stable. They're like a noble gas. Okay, so there's different bonds there. Let's do that. So an octet, okay, contains all the different electrons. So you're going to have multiple bonds to make everything have 8. Now there's one exception. Well, there's more than one exception. One of the main exceptions is hydrogen. Hydrogen does not have, remember the s, p, d, and f's? Hydrogen does not have an s orbital. I mean, it doesn't have a p orbital. So hydrogen is the duet rule. Hydrogen only wants 2 electrons to be stable. So hydrogen gas is H2, and it's got 1, and the one it shares with has 1 electron. So hydrogen has 2 electrons, and it's stable. Okay, so hydrogen is a duet rule. All the other elements are the octet rule. Hydrogen is very stable with just 2. So whenever we're drawing these Lewis structures, hydrogen is a terminal element. Once you put a hydrogen, you stop. You can only add 1 bond to a hydrogen. Can't take anything else because there's no more room for it. Has no more orbitals around it. Okay, so in drawing Lewis structures, the easiest way to do it is, okay, let's do the Lewis structure for water just to review. We've done this before, but let's do the Lewis structure for water. Water is H2O. Okay, the easiest way to draw a Lewis structure is to count your valence electrons first. Always do that first, and it's make life so much easier. Okay, so you have 2 hydrogens. You have 1 oxygen. How many valence electrons does hydrogen have?
1.
1, perfect. It has 1 valence electrons. There's 1 there. How many valence electrons does oxygen have?
6.
6, perfect. Okay, so 2 times 1 is 1, 6 times 1 is 6. You have a total of 8 valence electrons. So you're I'll see you later, Zeke. Okay, so that's what you got to match. You have to have 8 valence electrons. So we're going to make oxygen in the center, hydrogen, hydrogen, and then put the dots to make everything have 8. So just connect them by lines and then put your electrons around it to make it have 8. Hydrogen has 2 and the oxygen has 8. Okay, that's what you draw first. And then you count your valence electrons. We have count your electrons in this. This has to have 8 electrons here. So the free electrons, we have 1, 2, 3, 4, 2 in each bond. 4, 6, we have 8, right? We have 8 electrons. So that is the Lewis structure for water. Now they're not all that easy. Okay, so let's do a more difficult one. But that's just kind of review of one. Let's do urea. Urea is what's released in the urine that everybody counts with different disease and everything in the hospital. Urea is CH4 N2O. Okay. Now, what did I say the first step was? Count your valence electrons. We have carbon has how many valence electrons?
4.
4, perfect. Hydrogen is how many?
1.
1, and there's 4 of them. So we have 4 from hydrogens. Nitrogen is how many?
5.
You get and there's 2 of those, right? There's 10. Oxygen has how many?
6.
6. Hold on, someone's knocking the door. I got you back in 1 second. Hold on, guys. Hey. All right, I'm back. All right. They can stay here and watch TV if they want. They're- Be quiet. They're fine. All right. So now we got valence electrons. We got 4 from carbon. We got 4 from hydrogens. We got 2 from nitrogen, 10 from nitrogens, and 6 from oxygen. Okay. So we add up add those together. You have, where am I at? 12, 14, 24, right? So we need 24 valence electrons. Everybody see how we got 24?
Yes.
All right. Perfect. Good. That's half the battle. Whenever we're dealing with Lewis structures, carbon always goes in the center. That's our neutral compound. Most of our compounds are built around carbon. So carbon goes in the center. And then we've got oxygen, nitrogen. So we connect nitrogen, and we connect an oxygen. Okay. And then we have to have 2 hydrogens connected. There's ways to do it, but the way I would do it, and it just takes practice, you might draw different structures. Draw 2 hydrogens and 2 hydrogens and connect to that. So that's one possible structure. And we'll verify different things. If you do different ones, we'll verify what we call formal charge. And we'll get into that in just a little bit. Okay. But that's one way of drawing it, right? And then we make everything have 8. So we put all the things together and we make everything have 8 electrons around it. So then we add separate ones. Look at the hydrogens have 2, those are good. And then nitrogen, I'll put 2 dots right here. That makes it have 8, right? 2 above it and then 2 in each bond. So 2, 4, 6, 8. Carbon now it has 8. Nitrogen, now it has 8. Oxygen, now it has 8, right? Okay, now we count them. We've got, let's count all the dots first. 2, 4, 6, 8, 10, 12. Then each line 12, 14, 16, 18, 20, 22, 24. We have 26. Everybody see where I got 26 from by counting all my electrons? Does that make sense so far? Everybody see how I got 26?
Yeah.
Yes.
Okay, perfect. 26 does not equal 24, right?
Nope.
Okay, it's not right. So you got to change it. We have to make a multiple bond. We have to change some of these. So we, let's draw this out again. I think I can erase certain dots in this program. So we have nitrogen, and then we got carbon, oxygen, nitrogen, hydrogen, hydrogen. And I'm gonna make a double bond right there. Because I know how stable nitrogen carbon is. And you'll be able to do that if you did a couple of practice ones. This is a more difficult one. Okay. But the idea is to be able to count, now count the valence electrons. Count the free electrons, 2, 4, 6, 8, then count the bonds. 10, 12, 14, 16, 18, 20, 22, 24. This has 24 valence electrons. And that's your structure. Okay. We'll learn why I put the double bond there. Like I said, it has to do with formal charge. It just takes practice in doing it. But the big thing is to identify that you have to match the number of valence electrons. Okay? You count those first, then you draw a structure. You make everything have 8, and you go from there. That is one of the more difficult ones. Just to show you how it's done with a difficult one. We'll do another one from your book here. Let's do, okay. Let's do let's do perchloric acid, HCl. HClO, okay? A lot easier, okay? The ones that are terminal. Terminal means once you draw a bond to it, you can't have another bond. Hydrogen is terminal because they only have 2 electrons. So once you make a bond, it's done. The halogens, fluorine, chlorine, bromine, iodine, those are terminal also because they have 7 valence electrons around it. And once they accept one more, they have 8, they're stable. So they stop 2. So a hydrogen or a halogen, which is your fluorine, chlorine, bromine, can never go in the center because they can only have one bond. They're called terminal. Okay, so I have a hydrogen, an oxygen, and a chlorine. What's going in the center? Okay, can't use hydrogen in the center. Can't use chlorine. In the
chlorine.
No, that can't go in the center. That's terminal.
Oxygen
Chlorine,
then.
there has to be oxygen. Perfect. Because hydrogen and the chlorines are terminal. Hydrogen and the halogens are terminal. Okay, oxygen is going to go in the center. Now, let's count our valence electrons. Hydrogen is how many?
1.
Chlorine has how many?
It is 7.
Oxygen has how many?
It is 6.
Perfect. You guys got this part down pat. Add those
Yeah,
together.
I've done some of this chapter.
Good. This has 14 valence electrons. So our answer has to have 14. So oxygen's in the center. We draw hydrogen and we draw chlorine. Those are both terminal. And we put all the dots around it. Chlorine. Okay. That gives it 8, right? 2, 4, 6, 8 in the bond. And we make enough to have oxygen have 8. 2, 4, 6, 8. And then we count. Count the electrons in our structure. We have the free electrons, which are not in a bond. We have 2, 4, 6, 8, 10. And we have another one, 12. We have 14. We have 2 in each bond. Perfect. Let's do more of your chips.
I'll go ahead.
All right. That's our Lewis structure right there. That's it. Does that make sense?
Yeah.
Okay. There's always exceptions. You can have a whole book of exceptions to Lewis structures because you just can't create some that don't have electrons. In other words, let's do BF3, boron trifluoride. That's a B, not a good B, but it's a B. Okay. Okay. How many valence electrons? Boron has how many?
3,
3. Fluorine has
7.
7. 7 times, and you have 3 of them, so 21. So you have 24 valence electrons you have to account for. What has to go in the center? What did I tell you about the halogen, about fluorine? Or fluorine.
It's terminal.
It's terminal, perfect. It cannot go in the center. So what has to go in the center?
Boron.
Boron. Make everything have 8. Okay. Then count them. The 2, 4, 6, 12, 18, 20, 22, 24, 26, right? You got 26. That's not 24. Okay. So you make a double bond, right? No, you can't do that because there's a halogen. Remember I told you halogens and hydrogen are terminal. They can never have a double bond. All they can have is a single bond. So if you can't make this another multiple bond, you just got to erase 2 electrons. So we'd have boron because it just doesn't have it. They're not there. And you can't create electrons you don't have. You only have 24. So your Lewis structure for boron trifluoride would look like that. And that's going to make a difference in the shape of the molecule. Okay. We're going to get into that too. They're called the Vesper rules. We're getting the shape of how what they look like in 3-dimensional space. It's going to make a difference whether you have these electrons here present or not. Okay, make sure everything's writing here correctly. Perfect. All right. And the other exception I want you to know is the ones after you pass the first row, the first row on the periodic table, you got the second row with the S's and P's. After you're done the third one, you have extra orbits available because now you have 2 p orbitals around it, and those can be filled also. So there can be some exceptions. There's not a whole lot of exceptions, but it's these 2 I want you to know. Okay. Let's do phosphorus trichloride. So let's erase this. And we have phosphorus trichloride, and we're going to do phosphorus pentachloride. Right? So phosphorus, how many, phosphorus, why does phosphorus have to go in the middle in PCl3?
Because chlorine's terminal.
Perfect. Exactly right. Chlorines are terminal. Okay. So phosphorus has how many valence electrons?
Phosphorus has 5.
5 valence electrons. Chlorine has
Chlorine has 7.
7. 7 times 3 is 21. I have to count for 26 valence electrons. So we'll put chlorine or attached to the phosphorus. Just like that. We'll draw our lines first. Okay, just draw it out. And then we'll put in everything to make everything have 8. So let's put in our dots. That has 8 now. This has 8 now. This has 8 now. And this has 8 now. Then we'll count our dots. How many dots we got? 6, 12, 18, 20, 22, 24, 26. We got 26, matches 26. We're done. That's it. That's our Lewis structure. Once you match that, we're good. Now, PCl5. You said phosphorus has 5. You said chlorine has 7. So we have to have 40 valence electrons. Okay. This is a terrible 4. See if I can do that better. Not really. Okay. So you have 40 valence electrons. So what goes in the center again? Phosphorus. Now chlorine can only have a single bond to it. So once you draw chlorine, you have to stop. So chlorine stop, chlorine stop. Okay, and you have to have 5 chlorines around it. That's the only way you can do it, because chlorine cannot have a multiple bond. Like Cassandra said, chlorine is terminal. Okay, any halogen, fluoride, chlorine, bromine, iodine, all those in group 7 group 7A are terminal, and the hydrogens. Okay, so now let's put our dots around, make everything have 8. And the problem we're going to run into is, oops, can't really see that one. There we go. Now phosphorus, look at phosphorus. There's 10 electrons around phosphorus, which is more than 8. The elements in the third row across can break that rule because they have an extra p orbital. Remember, it's 2s, 2p, 6, and then 3p. So they can fill that extra orbital with bonds. So those are one of the exceptions. So let's count how many count our electrons in our compound. What do we got? So each one has 6 free ones on it. So 1, 2, 3, 6 times 5 is 30. And we'll start at the top one here. So 32, 34, 36, 38, 40. 40 electrons, 40 electrons. Bingo, that's it. So the exceptions are, if we don't have enough electrons, you can take some away because some things are terminal and you can't make a multiple one, like we did with boron trifluoride. And some things can have extra electrons, like phosphorus, and that third row across, okay, because they have an extra p orbital. Okay? And that's going to make different shapes of these molecules, which you're going to get into. So those are our Lewis structures. That's how we do it. That's how we count. Let me pick another one example from the book in here. Let's okay, let's do this one. Let's do a couple more examples here, make it fun. CH2.
I'm sorry, is this part of chapter 9?
Chapter
Yeah,
9.
it is.
Oh, it is?
Yes.
Oh, man. Okay.
Yeah,
thank you.
this is right on the beginning of chapter 9, section 1. And example 9.3 is CH2O.
Okay, thank you.
Right? Oh, no problem. Good boy. All right. So first thing we did is count our valence electrons. Carbon has how many?
4.
4. Hydrogen has?
Hydrogen has 1.
So there's 2 of them, so there's 2. And oxygen has?
Oxygen has 6.
6. Perfect. We have a total of 12 we need. So I always said carbon goes in the center. Draw a hydrogen to it, draw a hydrogen to it, draw an oxygen to it. And then make everything have 8. Whoa, how'd that happen? Let me do this so it looks a little bit better. All right. And then make this have 8. It has 6. Count your electrons. How many you get?
$14.
14. Perfect. What you got? Perfect. I got my granddaughter here. She's learning chemistry with us. Good. You can see your hand in the back waving. All right, so 14 does not equal 12. I told you it would be hard math. 14 does not equal 12. So what if they do? We make a multiple bond. Can we make the bond to hydrogen? Someone say no and tell me why.
Because it's terminal.
Very good. Perfect. Hydrogen is terminal. You cannot make the double bond hydrogen. So there's only one place you can make it. And that is on the carbon. Double bond oxygen. Now make carbon has 8 electrons around it. Oxygen is 2, 4, 6, 8. All right. How many electrons now? 2, 4, 6, 8, 10, 12. 12 equals 12. That's it. That's the Lewis structure for formaldehyde. Okay, and those are going to have specific shapes we're going to assign with our VESPA rules we're going to be doing a little bit here. It's not touchscreen. All right, let's everybody's understanding is pretty good. Let's do just a couple more for then move on to the next chapter, next section.
Are we gonna have a lot of these on the test? Because I like these.
Actually, there's like 2 or 3 questions of Lewis structures on the test.
Oh, okay.
Yeah. So let's do 2 more. And then we'll move on. Let's do hydrogen cyanide. Hydrogen cyanide is a great gas, extremely toxic, used in gas chambers. Always good for people. And CS2. All right, we'll do those 2. So what's the first step I told you to do? Count valence
electrons.
You got it. So hydrogen has how many?
1.
Carbon has
4.
4. Nitrogen has
5.
5.
Perfect. You guys are getting really good at this. 10. What I tell you about carbon? Carbon goes in the center. And I'll show you why it goes in the center when we do our formal charges. That'll make sense to you a little bit more. And then we draw 1 to hydrogen and 1 to nitrogen. And they make everything have 8. Okay. Now count your electrons. How many did you get, Izzy?
14.
14. Perfect. You got it. So does 14 equal 10?
No.
No. All right. So we have to make a double bond. So let's do H. And you can't make it with hydrogen, right?
Nope.
Hydrogen's terminal, so you make a double bond here to nitrogen. Now they make it have 8. Okay, everything has 8. Count your electrons.
12.
12. Still not. So make a triple bond. There goes 8. Count your electrons.
It's 10.
Bingo. You got it. That's it. That's what hydrogen cyanide looks like. Okay. That's why it's so deadly. Cyanide gas. The problem with cyanide gas is so strong because of that triple bond. Because oxygen's just a double bond, O2. So when you put the triple bond on there, it has a higher affinity for the hemoglobin red blood cells. So cyanide binds to the red blood cells where oxygen normally would bind, so the oxygen can't bind the red blood cell. So you die of asphyxiation because you can't get oxygen in your red blood cells because this binds so much stronger than oxygen. And that's how it works to kill people. Okay, CS2. Okay, carbon has
4.
Electrons has 4. Sulfur has how many?
6.
6.
So 12, 16 valence electrons. Okay, what goes in the center?
Carbon.
Carbon.
Perfect. Draw a line to sulfur. Draw a line to sulfur, and make everything have 8. How many electrons? Perfect.
Looks like there's 20.
Yep, you're right. You're exactly right. There's 20. 20 is equal to 16. So let's make a double bond. Get rid of some of these. So sulfur, carbon, sulfur. Let's pick this one. And I'll make a double bond here. Make a double bond. Make the electrons here. How many electrons now? Whoa. I did it. Look, I messed up. That doesn't count. That gave me too many around carbon. Yeah, now everything has 8. So how many now?
18.
18. 18 still doesn't equal 16. Make another double bond. Make it on the other side. Now count.
$16.
And 16 equals our starting point. Okay, 16 equals 16 right here. That's it. This is the Lewis structure for CS2. You guys got it. Perfect. And I have to move this up just a little bit. Let's I'm going to slide this up a little bit. We'll be in good shape. Here we go. All right. Now, you see me do a couple things that, like moving things around. Like you could have a Lewis structure like S, C, triple bond S. Yeah. And that would still work. That would still give you, let's see, 2, 4, 6, 8, 10, 12, 14, 16, right? So this still has 16 electrons, and this has 16 electrons. The reason it's this one and not this one is because of formal charges. Okay, and formal charges is a formal charge is you count the number of valence electrons it's supposed to have, and you subtract every free electron and every bond. That's it. That's how you do a formal charge. So it sounds worse than it is. So let's get this clear here. Okay, and let's do hydroxide. Hydroxide is OH minus. This is like one of your polyatomic ions. That's hydroxide. Okay. So let's do it simple. We'll get into more complicated ones as we go on for a second here. So hydrogen, OH, the Lewis structure is oxygen bonded to hydrogen. Okay, everything has 8. Okay. When we do things with a charge, put brackets around it and put the charge. Okay. The formal, now we look at formal charges. So there's our Lewis structure. Okay, the formal charge of hydrogen. What's the valence number of electrons on hydrogen? What's its normal valence electrons?
1.
1. And it has 1 bond, so -1. So the charge is 0. So hydrogen here has a formal charge of 0. You subtract every free electron and every bond. If you have 2 bonds, you subtract 2. You have 3 bonds, you subtract 3. You have 1 bond, you subtract 1. If you have 4 electrons around it, you subtract 4. Okay, now let's look at oxygen. Oxygen is normally what?
6.
Oxygen is normally 6. How many electrons do we have around oxygen? Electrons, not bonds, just 3. How many dots do I have?
6.
6. -6. And how many bonds do I have to it?
2.
1.
No.
I got 2.
Yeah, we have 2 electrons in that bond. We only have one.
That's 1.
Bond, though. We're subtracting every free dot. We're subtracting every electron that's not in a bond, and then the number of bonds, and -1 bond. And that comes out to -1. So the formal charge on oxygen is -1. And here's your charge right here. That's where compound has a -1 charge.
I have a question because I was doing a bunch of chapter 9 today. I was already doing the Lewis structures, and then I come across one of these already, and I already knew that there had to be brackets around it, right? But it didn't give me like the tool to even enter any brackets, so there's no way possibly I could get it right.
No, you just enter without the brackets.
Yeah,
enter without the brackets.
Okay, well,
But you'll see.
yeah, what?
Go ahead.
Sorry. Well, yeah, well, I didn't even bother pressing it because I was like, well, I need the brackets, so I know I'm gonna get it wrong. So I was like, maybe there's like another thing, or maybe
No,
I guess just leave it as it is.
leave it as it is. Though when you see me do it, I'll put brackets around it because you're supposed to.
Okay, that makes sense.
All right, so that's how you do formal charges. Let's do another. Oh, we're done. It's gonna be. I want to do one that's gonna do that, but I don't see one right there yet. So, let's do acetate. Okay, your acetate ion. So let's clear this. It's going to give me another example of something. It's C2, H, how many hydrogens? H3O2. Okay, so how many valence electrons? Carbon has how many?
4.
Okay, so it has to have 8. Hydrogen has 1, right? So there's 3. Oxygen has
12.
12, because there's 2. Perfect. Okay. And yeah, that's not what I wanted to do. That's okay. 4, 3, and 2. Okay. So we're going to put our carbons in the center. So carbon to carbon bond. Okay. Then we have 2 oxygens. We'll bind at the end here, oxygen, oxygen, and then 3 hydrogens. Okay. So we've got, we're gonna have to cut one off. This has an odd number, so we'll do one of the Lewis structures here for you, and then I wouldn't use something like this to be on a test, but we'll count all that, count all that. There, everything has 8 electrons around it, right? Oh, it's an, I'm sorry, negative charge. It's acid has a negative charge, so we add 1 for the negative charge, so that's 24. Okay, so we need 24 valence electrons because this is a negative ion. Okay, so if we do, okay, let's get rid of all that first. I want to get rid of that charge. Okay, so this is 24 because there's 1 electron. That account for the electron. Sorry about that. That's acetate's -1. All right, so we do that, and then we have okay. How many electrons there? How many valence electrons we got? 2, 4, 6, 8, 10, 12, 14. How many is it?
2, 4, 6, 8.
26, right? Perfect. Got it. We have 26. So we have to get rid of some electrons. So our structure looks like, make a double bond. And there we go. If we count all those, we will have 24. Okay, there's our Lewis structure. Okay, let's do formal charges. What's the formal charge on hydrogen? Hydrogen normally has 1, right? 1 valence electron, and we got 1 bond attached. So 1 minus 1,
0.
0. Formal charge on this hydrogen is 0. Formal charge on this hydrogen is 0. Formal charge on carbon. Carbon normally has what? What's our valence electron number from the periodic table?
4.
4. And how many bonds do I have attached to it? I have 4 bonds attached, right? So 4 minus 4 is 0. This carbon has 4 bonds attached to it. It's 0 also. This oxygen. Oxygen has 6, right? How many dots do we have? And then how many bonds we have? 1. So 6 minus 1 is -1. On this oxygen, oxygen is normally 6. We have 4 dots, so 6 minus 4. Let's do it this way, do 6. And then -4 for the dots, for electrons. And then -2, we have 2 bonds to this one, a double bond. 6 minus 4 minus 2 is 0. Okay, there's your negative charge. And we have a formal charge of -1 of that oxygen. Now, the reason this is important is that's how come I know to draw it that way. Why couldn't I have drawn, let me do something a little different color here. Let's do green, I like green. Why couldn't I have gone C, bonded to O, bonded to C, bonded to that one on there. We'll do 2 dots there, so it'll work. Let's not do 2 dots. We don't need that. Just gonna do this. 2 dots. CH, CH, CO, CH. Kind of ran out of room there. Okay, count your valence electrons in there. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, we have the correct number, right? So why is this wrong and this right? Because you have to have the formal charges the least number possible. Okay, so let's do formal charges. On this one, it's 0. This one is 0. And this hydrogen is 0. All right. What's the formal charge on this carbon? It's supposed to be 4 and 4 bonds. So it's also 0. So far, we're really good. Okay, oxygen. Oxygen is supposed to be 6, right? 6. So we've got 6 minus 2 dots, right? And how many bonds we have on it? Oh, that's a line. So that's not a dot. And we have 3 lines, right? So 6 minus 2 minus 3 is positive 1, right? So this oxygen has a positive 1 charge. What about this carbon? It has 4, and then minus 4 dots is 0, and then minus 2 lines is minus 2. What about this oxygen? We have 6 minus 4, 6, 1. 6 minus 4 is 2, and then 2 dot, that one's 0. Okay, but our charges here, we have a negative 2, and we have a plus 1. Okay, this one we only have a negative 1. It's right here. So this one is more stable. That's why we draw it that way. That's why we use formal charges. It tells us how we can draw our Lewis structures. And you can draw a whole bunch of ways, but you have to do it that it has the lowest formal charge. Okay, and again, your formal charge is your number of valence electrons in your neutral atom, which you get right from the periodic table. Subtract the number of covalent bonds, so every bond, and subtract the number of unshared electrons, the electrons that are not in a bond. Okay. So let's do another example of, that's what we did, that's when we do the charge for, let's do sulfur CSN, cyanide again, okay? Now we could do the Lewis structure of sulfur bonded to carbon to bond to nitrogen. Well, the sulfur is how many valence electrons?
6.
Sulfur 6, carbon is
4.
4, nitrogen is
5.
5, and CSN is negative 1. So we add 1 electron, right? So every charge, if it's a positive charge, you take away an electron. If it's a negative charge, you add an electron. So that's 10, 15, 16 we have to count for. So let's put our dots here, put our dots here. And that's 2, 4, 6, 8, 10, 12, 14, 16. And again, brackets and a negative charge is how you'd see it. Okay. Now, why couldn't I have done this? Like that, put the double bond and just share the double bond. Count your electrons. 2, 4, 6, 8, 10, 12, 14, it has 6 electrons. Why is one wrong? Why is this one wrong and this one not? Okay, formal charges. Do nitrogen, like I said, it just takes practice to do it. This is why we draw it certain ways. What's the charge in this nitrogen? This nitrogen is nitrogen normally 5. How many dots do we have? We have 2 dots, we have 3 bonds. Comes out to 0. Carbon. Carbon is normally 4. We have no dots, but we have 4 bonds. 0. Sulfur. Sulfur is normally 6, and we have 6 dots and 1 bond, negative 1. So we have a negative 1 formal charge on sulfur. Let's look at the other one, nitrogen. Nitrogen is normally 5. How many dots we have? We have 4 dots. Perfect. And we have 2 bonds. 5 minus 4 minus 2 is -1. Okay, carbon. 4 and no dots. We got 4 bonds. Carbon still 0. And sulfur. Sulfur is normally 6. And we got 4 dots. And we got, wait, 1, 2, 3, 4. And we got 2 bonds, right? So that's equal to 0. Okay. But actually that works out where it's the same either way. So if you put that on an exam, I would accept either one as a valid Lewis structure. This is the correct one because of different stability, but with formal charges, that's how we determine it. Okay. So that's how you calculate a formal charge. Let's move this up. Let's see. Okay. Let's do one more for formal charge just to make sure we understand everything. Let's do azide. Azide is what they put in, sodium azide is what they put in airbags, which makes things that explode in your face extremely quickly. It's a really explosive compound. Once it's activated, once you have to force any kind of electroignition, you hit the front of the car hits the electrical signal of this airbag, it ignites azide and it instantly inflates your airbag. Okay, azide is N3. Okay, the Lewis structure for this, we'll just draw it out for you, is nitrogen, and then make everything have 8. All right, that's the Lewis structure. What are the formal charges? That's like a typical test question. What's the formal charge on this nitrogen, and on this nitrogen? Okay, so the first one to the left. Okay, nitrogen is normally 5, right?
Mhm.
So subtract the dots, subtract each valence electron, that's -4, and subtract the bonds, -1. Nitrogen is normally 5, and there's no dots, no free electrons, unpaired electrons, and there's 4, okay, plus 1. And this nitrogen will be the same, 5 minus 4 minus 2, -1. So if I put 1, 2, 3, the question would say, what is the formal charge at the nitrogen where the number 2's at, with the element where number 2's at? And the answer should be a +1. That's how you see the question on your exam. Make sense?
Yeah.
Okay.
Yeah.
Formal charges are your valence electrons, like your neutral atom right from the periodic table. Subtract 1 for every unpaired electron. Unpaired just means not in a bond. And then subtract 1 for every covalent bond. That's how you do formal charge. So let's see what formal charges, that's all good. Those are good. We did Lewis structures, polyatomic ions. We did that. Let's do CH3S. Okay. Let's do one more here at example, then move on to the next section. CH3S minus. Whenever you have negative, you know you're going to have some kind of formal charge on it. So carbon, hydrogen, 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 sulfur. That's it. Make it have 8. And let's count our electrons. Carbon is supposed to have 4, right?
Yeah.
Hydrogen has how many?
1.
1, and there's 3 of them. Sulfur has how many?
6.
6.
And we have one valence, one negative charge, so 1. So that comes out to 8, 6, 14, right? You got to have 14 electrons. So count our electrons, what we have here. We have 2, 4, 6, 8, 10, 12, 14. Okay. Does that look right? That's our Lewis structure. Now it says, also check any one that has a formal charge on it. Okay. What's the formal charge on this hydrogen right here?
Would it be 0?
It'd be 0. What's the formal charge on this one?
0,
0. Formal charge on this one.
0,
And formal charge on carbon.
0,
What's the formal charge on sulfur? 6. Minus how many dots?
6,
Minus covalent bond, which is only has 1. So the formal charge is -1. So everything's 0 except sulfur, which has a -1 charge in this one. My computer's running out of power. I was using it. Plug that in. Okay. All right. So that shows you the different formal charges. Okay, can't do that. Let me see what they got here. Okay, let's do the compound. Let's do one more example here and compare. Which would be the other, if I gave you 2 Lewis structures, which one would you say would be correct for the compound CCl2O or COCl2? COCl2. No, I got that wrong. I put CO2, 1 chlorine. All right, let's draw one Lewis structure, which would be carbon, double bond to oxygen, bonded to oxygen, bonded to chlorine. Okay, and the other one would be carbon, okay, bonded to oxygen. I'm trying to look at the double bond to chlorine. I can't, I'm having a hard time seeing this one. It was, okay, hold on a second. Restart this. It's COCl2. That's where we're having the, boy, I'm having trouble seeing something. Yeah, COCl2. Which structure is more correct? Okay. COCl2. Okay, so carbon double bond to oxygen bonded to 2 chlorines. Okay. Or carbon single bonded to oxygen bonded to chlorine and double bonded to chlorine. Now, which one you say is more correct? One on the left, one on the right. What did I tell you about chlorines? The halogen.
Mm-hmm.
They can only have a single bond. So this is,
So that'll be the left.
yep, that's your correct structure. Now, the reason is that's because of formal charges. So what's the formal charge on this chlorine right here? Chlorine's normally 7, right? We have 6 dots around it and 1 bond. So 7 minus 6 minus 1 is 0. Charge on this one?
0,
Thing. Carbon, normally 4 bonds around it, it's 0. Oxygen, normally 6. We have 4 dots, 2 bonds. 6 minus 6 is 0. Every one of those elements has a 0 formal charge. Okay. Let's do this one. Carbon still has a 0 charge. This chlorine still has a 0 charge. This chlorine, it's normally going to be 7, and it's got 1, 2, 3, minus 4. Okay. Because of each dot, each bond, and then each bond is 2. So this is going to be positive 1. This oxygen, normally 6. Minus 6 for each dot around it, and then minus 1 for the bond is -1. So this has a positive 1 and -1 formal charge. It's not going to be near stable. This is going to be your correct Lewis structure. And this is not correct because that but on the form, you could tell it right off the bat. Okay. And there's one more thing we need to talk about, and that is Lewis structures. Lewis structures have what's called resonance forms or resonance structures. In other words, if we take a resonance structure, we make a multiple bond, and we could do it in different areas. So let's take NO3 minus. We can't write that. Nitrate ion, NO3 minus. Lewis structure, nitrogen is 5, oxygen is 6, negative charge is 1. 24 valence electrons. We have to count for 24 electrons. So nitrogen goes in the center. Here we got an oxygen going to each one. And then let's make everything have 8. Okay. Now, how many electrons around our structure? How many dots we got, and then how many, 2 in each line?
Twenty-six.
26. That's not 24. So we're gonna make a multiple bond. So let's do this. Okay, now count. Who gets 24?
24.
Right, perfect. No, that's the Lewis structure. But why couldn't I have done this? And why couldn't I have done this? Okay, all 3 of those are right. This is what's called a resonance structure. It makes something extremely stable. And they don't exist as 3 ones in nature, they share it. In other words, what actually is in nature, a resonance structure is, I'm not gonna put all the dots on this, is 1 1/3 bond. It's kind of shared. It's called a hybrid. It's shared between each one. Okay, it just causes, it has the strength of 1 1/3 bond. And it's just shared between them. Okay, but it's called a resonance structure, and they're extremely stable because of this resonance formation they have. Okay, even though let's do the formal charge on it now. Let's do the formal charge on oxygen, on oxygen, on oxygen, and nitrogen. Okay, so this oxygen here, the one on all the way to the left, oxygen is normally 6. We got 6 dots and 1 bond. So we got a -1 charge, right? It's normally 6. We got 6 dots around it and 1 covalent bond. So 6 minus 6 minus 1 is -1. Nitrogen. What's the formal charge on nitrogen? Somebody tell me.
5.
Right, it's 5. Okay, what's the formal charge? That's the number of valence electrons. That's right, perfect. So you got 5 valence electrons normally. So what's the formal charge now?
Would be +1.
It's perfect. Exactly. Very good. It'd be +1 because 5 is your normal charge, like she said, and then you have 4 covalent bonds and you have no unbound electron pairs. So you got 4, you got 5 minus 4 is +1. And let's see, let's do this oxygen on the top. Oxygen on the top is going to be also, it's going to be 6 minus 6 minus 1. So it's going to be -1. Okay. And about this last oxygen here.
0.
6 minus 4 minus 2. Perfect. So you've got a -1 formal charge, you got a -1 formal charge, and a +1 formal charge. So the net charge is -1. That's where that negative comes from. So even though you have a lot of formal charge on this, you've got stability because of what's called a resonance structure. It can be drawn in different ways. Okay. Any questions on that?
No.
Perfect. All right, now we're gonna go into shapes. This is this is real important in the medical profession because every drug that we have, it works by binding to receptors in the body. And it binds to receptors in the body by shape. Okay. Once it bonds with that, the receptors are traded, and we get analgesics, we get antibiotics, we get all kinds of things that bond because of a certain shape. It matches. Okay. And you have to determine the shapes by determining the geometry of the electrons that are around an object. Because remember, electrons, every bond around an element, okay, is going to move itself to be farthest away as possible because they're both negative. So if you've got, let's clear this again. If you got carbon, let's just do water, H2O. Okay, H2O is not going to look like this. Okay, because all the bonds are negative charges. So there's two bonds and there's valence electrons. So the negative charges, because like charges repel. And that's the whole concept of VSEPR. Valence, shell, electron pair, repulsion. All that means is the valence electrons, okay, are going to push themselves away as far as possible. Okay, if you have hydrogen, let's do the Lewis structure for HCN. We did that. Hydrogen, carbon, nitrogen. Okay, the geometrical form is going to be linear. It's going to be a straight line because that's the farthest away these can push. Okay, if it pushes closer by any other degree, it's going to make one closer than the other. They're going to push it away as far as they can. Okay, you have two types of geometry we're looking at. We're going to look at electron geometry, and we're going to look at molecular geometry. In other words, what's the shape of the electron pattern? And in that, you have to consider the non-bonding electron pairs, okay? And what's the shape of the molecule without considering the non-bonding electron pairs? What's the molecule actually look like? Okay, so let's look at, let's do another one. Let's do CO2, carbon dioxide. Let's draw the Lewis structure. There's our Lewis structure. Okay, if the central atom, because you have to do everything around one atom. If the central atom has no non-bonding electron pairs, the molecular geometry equals the electron geometry equals the molecular geometry. Okay, if this central atom has no dots around it, then the molecular geometry and the electron geometry are the same. Okay. So CO2 has two things attached, carbon in the center, and has an oxygen and an oxygen. You know, it has those bonds. Okay, so it's going to be 180 degrees. There's nothing to distort it. That's what's called linear. Okay, let's do carbon, oxygen, hydrogen, hydrogen. Again, how many free electrons are around the central atom? None. There isn't any. Okay, so you have your electron geometry. It's going to be 3 points. Okay, so it's going to spread out evenly to push everything away as much as possible, and that's going to be 120 degrees because there's 360 degrees in the circle. So the angle between the carbon and this angle here is going to be 120 degrees. And this is what's called pyramidal. It's called trigonal planar. Okay, so this is trigonal, which it's 3, and it's planar. It's all in one plane. Okay, the electron geometry is trigonal planar, and the molecular geometry is trigonal planar. They have to be the same. Now let's do one that they're going to be different. Okay, let's do NO2. NO2 is nitrogen, bonded oxygen, bonded oxygen. Okay. And there's a negative, this is our negative charge, -1. Formal charge on this oxygen is -1 to the left. So, okay, we got 2 bonds, we got electron pairs here, and electron pairs here. Okay. Now we have electron pairs on the central atom. So you've got 3 negative charges. You've got a negative charge here. You got a negative charge in that bond. You got a negative charge in that bond. So you have 3 negative charges. So they're going to push apart to minimize the repulsion between each other. You can have an oxygen bonded to nitrogen, bonded to oxygen, and then those are negative charges here. Okay. Now the only non-bonding electron pairs we're going to worry about are what's on the central atom. Okay. So the electron geometry.
Would it be bent?
The electron geometry is going to be trigonal planar. That's the electron geometry, because you include this electron pair right here. The shape, the geometrical shape, the molecular geometry is going to be
bent.
Perfect. Bent or angular, same thing. Okay. So the electron geometry is different than the molecular geometry if there are non-bonding electron pairs on the central atom. Okay. Then you got to count the negative. It's just, all it is negative charges pushing each other apart as far as they can, trying to get away from each other because they repel.
Yeah, I kind of recognize these from, I forgot which chapters because I skipped ahead and I did 13 and 16, but I've done these now.
Okay, good. Perfect. So let's do another example of, let's do water. Okay, water is, everybody knows H2O, right? Your Lewis structure is hydrogen, bonded to oxygen, bonded to hydrogen. Okay. Central atom has non-bonding electron pairs. So how many negative groups are around my oxygen? There's a negative group here. There's a negative group here. There's a negative group here. And there's a negative group here. Perfect. So there's 4 negative groups. 4 negative groups means the electron geometry. Electron geometry is going to be what's called tetrahedral. D-R-A-L. H. I can't spell. Can't write it right. Tetrahedral. There we go. All right. Because oxygen has 4 groups around it. So it's going to have 1 group here, there's oxygen in the center, 1 group coming out of the board, 1 group here, and 1 group going into the board. Okay, that's 1 group straight up, 1 coming out, 1 going back, and 1 in the same plane. Okay, I can't draw 3-dimensional to save my life. Okay, but every one of these angles is 109.5 degrees. That's 4 angles. It looks like line coming up, looks like a pyramid with 3 points and then a line coming on top of it. That's how it's spread out. Okay, and that's called tetrahedral. Now, that's the electron shape. What's the molecular shape? The molecular shape, you only count where there's attachment. You do not count the non-bonding electron pairs anymore. They're still there, influencing shape, but we have a hydrogen here and a hydrogen here. So this is our shape. So the shape is bent. The molecular geometry is bent. The molecular geometry is bent. The electron geometry is tetrahedral. And there's one more I consider. NH3, ammonia. NH3 is nitrogen, hydrogen, 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 and 2 dots. So you have an electron geometry of tetrahedral. We have 4 things around it. Okay, there's 4 negative groups. So the electron geometry is tetrahedral. The shape, which is our molecular geometry, I lost the E there, okay? You only have the 3 things here. You have nitrogen, you have 1 hydrogen, you have another hydrogen coming out this way, and another hydrogen going back into the board. Okay, so we only have 3 shapes. So if we take that top one off, this is what's called a trigonal pyramidal.
Planar. Yeah.
No, not planar. This, because this have different shapes. This goes back and forth. The trigonal planar, put them on the same day, but we have this here, Trigonal planar exists if you have no non-bonding electron pairs. Trigonal pyramidal is when you have a pyramid, which is a basically 3 points of a pyramid base stacked on top of each other. It's a three.
Oh, yeah, I
shape.
can see it now from the shape.
Yeah, it's a trigonal pyramidal. And those are all the shapes we got. So if we do one of the, let's do one of those questions here. We got that, we got that. Trigonal planar, tetrahedral. All right, so let's do an example of, okay, let's draw this little structure, hydrogen, carbon, hydrogen, okay. Let's double bond to a carbon, bond to a hydrogen, and then bond to another carbon, double bond to an oxygen, double bond to an oxygen, bond to a carbon, bond to 3 hydrogens. And I would put numbers at, remember, you only do this around a central atom. So let's put numbers 1, 2, 3, 4, and 5. Okay, what's the, I'm gonna make a chart here. We're gonna do electron geometry and then shape, the actual molecular geometry, what the shape of the molecule is. And number 1, what is the electron geometry? Okay, remember if there's 0 non-bonding electron pairs, there's an electron right up here, actually, okay. If there's 0 non-bonding electron pairs, the molecular geometry equals the electron geometry. So look at number 1, what's the electron geometry? How many negative groups do you have?
Is it 4?
No, not groups. You have 4 bonds. But you have a group here, a negative group here, a negative group here, and a negative group here. So you have 3 negative groups.
Oh, I see.
Okay,
See, because I counted the one right there as separate when it's together.
it's together. It's you're grouping everything to according to in space. Double bonds, triple bonds are all together. So what's the electron geometry? Three bonds with no, 3 groups with no non-bonding electron pairs would be trigonal planar.
Planner?
Yeah.
Okay.
Trigonal planar. Okay, and the shape would be trigonal planar. Okay, look at number 2. How many groups are there?
3 is, wait, let me see.
How many groups?
Yeah, 3 as well.
You're right. So what's the electron geometry?
So it's trigonal planar.
Trigonal planar. What's the shape?
Looks kind of bent, even though it's the,
Well, there's 3 attachments
so I'd say trigonal planar.
on a planar. Remember, if there's 0 non-bonding electron pairs, it has to be the same. Number 3. What's the electron geometry?
3.
There's 3, so what's the electron geometry? There's 3 groups.
Trigonal planar.
Trigonal planar. And what's the molecular geometry, the shape?
It's 3, so trigonal planar.
The planar, perfect. Okay, now we're gonna vary it up. What's the number 4? What's the electron geometry? How many groups do we have counting all the electrons? How many groups do we have? Negative.
Seems like 2.
No, you got a group here. You got a group here. You got a group here. And you got a group here.
Oh, it's 4 then. Okay.
Okay.
Let's
So,
see.
so what's 4 for the electron geometry? They saw the already walked through it, saw the dog.
Yeah.
Remember, what's 4 electron geometry? If there's 4
Would it
groups,
be tetrahedral?
tetrahedral, perfect.
Okay, I got it.
Got it? Good. And what's the shape now?
Let's see.
What would the shape be?
Kind of looks trigonal pyramidal, the shape.
No, trigonal pyramidal would have 3 bonds and then a non-electron pair on top. This only has 2 bonds because you don't consider this, you don't consider this. Remember, you only consider the things that have bonds to it. So you have 2
So then
bonds.
you're saying it'd be linear or bent?
I'd say be bent, definitely.
Bent, okay.
Yep, perfect. It'd be bent. It can't be linear because there's non-bonding electron pairs. If you ever have non-bonding electron pairs, you can't be linear because they're going to distort it. And one more. How many groups are there? Negative groups are there? On that carbon, how many negative groups are there bonded to it?
Would it be 4?
Yeah. So what's the electron geometry for 4 bonds?
Tetrahedral.
Tetrahedral, perfect. And what's the shape?
Trigonal planar.
No, there's no non-bonding. Remember, the shape and the electron geometry are the same if there's no non-bonding electron pairs. Then nothing to push it apart. So are there any non-bonding electron pairs on carbon? There's just 4 bonds, right?
So it'd be tetrahedral.
Tetrahedral as well. Perfect. You got it. Good. Determining electron geometry. Let me see how many examples I got here. Let's do aspirin, because chemistry gives everybody a headache, right? Let's do salicylic acid. And I'll draw the Lewis structures. We'll never get this one. But we've got carbon, and we're in a ring structure here. Carbon, 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 carbon. And this is a benzene ring, right? Yeah, so I got double bond, double bond, double bond. Okay, and then we got carbon, double bond to oxygen, double bond to unbonded oxygen, bonded to hydrogen. Okay, and this is an OH group on this carbon. Okay, salicylic acid. Let's do 1. I should put the hydrogens on here too, so it doesn't confuse everybody. Hold on. Let me add your hydrogens. Everything has 1 hydrogen here. That one doesn't. I'm missing something. What am I missing? I'm missing something. Still works. I'm still missing hydrogen somewhere. Come on in. Hold on. Don't let the dog out, guys. All right. So here we go. We got 1, 2. Let's put a 1 right here. Let's put a 2 right here. Let's put a 3 right here. And here's another hydrogen. That's what I'm missing. There's a hydrogen. Anyway, I couldn't see it there somewhere. And put a 4 right here. And put a 5 right here. So let's do those 5 points. All right. So number 1. Okay, we're going to do electron geometry. And we're going to do molecular geometry. Okay. So let's do, where did I put number 1 here? Okay, so I put number 1 right here. Number 2, 3, 4, and 5. All right. So number 1. Okay. Everybody see number 1? How many bonds to that carbon?
Three.
Yeah, there's 3 negative groups. Okay, there's a group here, a group here, and a group here. So 3 groups to that carbon. So what's the electron geometry? three groups, three groups of
Monoplanar.
trigonal planar. Perfect, because there's no non-bilateral pairs. So this is trigonal planar. What's the shape?
Trigonal planar.
Trigonal planar. Perfect. Again, if there's no non-bonding electron pairs on that central atom, the shape and electron geometry are exact same thing. Number two, where to put number two? Right there. Okay. Number two. Okay, again, what's the electron geometry?
Trigonal planar.
Trigonal planar. What's the shape?
Trigonal planar.
Okay, perfect. You guys are getting this. Number three. Okay, what's the electron geometry? Okay, now you've got non-bonding electron pairs. How many groups? How many negative groups around it?
4.
4. Okay, so that's what? What's 4 groups around it?
Tetrahedral.
Tetrahedral. And what's the shape?
Hold on, my screen's acting up.
My screen or your screen?
No, yeah, your screen. I don't know why on my side it keeps, and then my mic wasn't working earlier for a few seconds.
Is it working now?
Mm-hmm.
Okay.
Just trying to, keeps blurring.
Huh. Could be the connection here. So number 3 was tetrahedral, right? What's the shape?
Yeah.
So the electron geometry is tetrahedral. What's the shape?
Linear.
Not linear.
It's bent.
Bent. There's 4 points to it.
Nice.
If there were no non-bonding electron pairs, that would be linear. But if it's bonding pairs, they'll exist. So it's 2 points to a tetrahedral, which is a bent shape. Okay, number 4, electron geometry. That oxygen.
Trigonal planar. Oh,
You got a group here, a group there, a group there. So 4 groups. 4 groups is what?
Tetrahedral.
Tetrahedral. Perfect. So it's tetrahedral. And what is the shape?
Tetrahedral.
No, not the shape.
Bent?
Electron geometry is tetrahedral. What's the shape?
Let's see.
Is it bent?
Yep, it is a bent. 2 parts to it. Perfect. And one more. Number 5. What's the electron geometry? That's just an arrow. That's not a bond. Electron geometry is what?
Three.
Perfect. And what's 3? What's it called?
Trigonal pyramidal.
Not pyramidal,
Planar.
planar. If there was non-bilateral pairs with 3 groups, then it would trigonal pyramidal. There's no non-bilateral pairs, so this would be trigonal planar. And what's the shape?
Bent.
There's 3 groups, remember? There's a group here, and group here.
So trigonal planar.
Trigonal planar. Remember, if there's no non-bonding electron pairs, there, then the electron geometry is the exact same thing as the molecular geometry of the shape. Does that make sense?
Yeah.
All right. And one more section. That is on polarity. I haven't finished this chapter. We're going to talk about electronegativity. Electronegativity is a big word, and all it means is how much it wants an electron. That's it. Because every bond is a pair of electrons. Certain elements are going to draw electrons closer to them than other elements. Okay. Fluorine is the highest. Francium is the lowest. Goes across the periodic table. Top right is the highest. Bottom left is the lowest. There's numbers on your periodic table. And in your book, you'll have a chart. In my data, I don't know, it's in your data packet. You'll have, I think you'll have an electronegativity chart. But in the book, they give you one. Okay. Blow it up here. And I'll give you some examples what they say on it. It says fluorine is equal to 4.0. Chlorine is 3.0. Bromine is 2.8. Let's do oxygen 3.5. Nitrogen's 3.0. And boron is 2.0. Just an example of some of them there. Okay, that's from your table there. Table 9.2. Right? It's just how much something wants an electron. It's called electronegativity values, and we use this to predict polarity. In other words, if you had a bond between nitrogen and oxygen, all right? Now, nitrogen is 3.0. It's a measure of how much it wants the electrons, and oxygen is 3.5. So oxygen wants electrons more. So the bond is going to be polar. In other words, the electrons are going to be pulled in this direction. So there's going to be a little negative charge this way. This is delta in Greek letters, and a little positive charge this way. Because if the electrons are dead center, there's no charges. But the higher electronegativity value, and again, all it means is how much it likes electrons. The higher it is, the more it's going to pull those electrons towards it. If it pulls it towards it, it makes it more a little negative and leaves it a little positive where they pull the electrons away from. Does that make sense?
Yeah.
Okay, that's all. Don't get confused with electronegativity. It's a big word, and all it means is it likes electrons. And there's numbers with it. So there's no, you can tell what bond is polar and non-polar, okay? So when we're doing this, you can say which, let's have a nitrogen oxygen bond. Let's have a nitrogen fluorine bond. And let's have a boron. Let's have a oxygen chlorine bond. Okay. Which one of those bonds is the most polar? Okay. So nitrogen, we said, was 3 and 3.5. So we've got a difference here of 0.5 in polarity. Nitrogen was 3, fluorine is 4. So this is 3.0, 4.0. Okay, a difference of 1.0. Oxygen was 3.5. Chlorine was 3.0, difference of 0.5. So look at your numbers. Which one of those three is the most polar bond? Which is the biggest number?
1.0.
Yeah. So your nitrogen fluorine bond is the most polar bond. It's got the greatest difference between the two where they pull electrons apart from each other. All right. Now, when we do that, we have different types of bonds. We have covalent bonds. We have ionic bonds. Those are two we talked about already. Now we have polar bonds. So basically, a covalent bond is when your electronegativity is less than 0.5. There's not much difference. That's called a covalent bond. Basically, there's no real difference under 0.5. Ionic bond is greater than 2. So anything in between 0.5 to 2 is a polar bond. Well, there's a difference between that. When you do the polarity of the bond. Okay. So let's do an example. We'll do it from the book. We have a carbon-oxygen bond. And we have a fluorine sulfur bond. All right, and they want to know which is more polar and show the direction of polarity. We'll show you we do that in different ways here. But first of all, what is carbon? Carbon is, look at the electronegativity on your table. What is carbon? Everybody see the numbers I'm looking at?
No, I don't.
Okay. Look at table 9.2 in your book, or my data table has my data packet should have it in there. On the periodic table, it'll show you the electronegativity value. But if you look at the values on the table, carbon is 2.5. Oxygen is 3.5. So what's the difference? The difference between this is 1.0. Fluorine is 4. Sulfur is 2.5. What's the difference? 1.5. So which bond is more polar? Fluorine sulfur or carbon oxygen?
Fluorine and sulfur.
Fluorine sulfur. Perfect. Okay. Now, this is your more polar bond. How we show direction. We draw a little arrow and we point to the more electronegative one. So you can draw a little arrow on top. The arrow goes this way, and then you put a little plus sign on the other end. That means a positive carbon and a negative oxygen as opposed to electrons towards itself. That's how we indicate it. Okay? Because this was delta plus, remember? This was delta minus. Fluorine and sulfur, we draw a line again. You put the arrow going towards the more electronegative one, and then the plus sign over the sulfur. How we indicate what they are. Okay, let's do a couple examples from your book here. And they said, well, find the electronegativity between each of the atoms and call the bond polar, covalent, or ionic. Okay, first one is carbon, oxygen. Okay, what's the value of carbon? I put the bonds down here. All right, there's your bonds. Okay, so we look at carbon. Okay, it's table 9.2 in your book. You want to look at the different values. It might be on my periodic table too. Let me take a look. Do I have electronegativity up here? Oh, here, right here. It's on the data table, right? Electronegativity values. Here's the values right there for you, right? So that's where we're getting the values from, okay? So let's go down to carbon, oxygen. Carbon is 2.5. Oxygen is 3.5. Carbon is 2.5. Oxygen is 3.5. The difference is 1.0. Okay, everybody see where the numbers are coming from now?
Yes.
Okay, good. I'm not just making numbers out of thin air. Okay, nitrogen and hydrogen. Nitrogen is 3.0. Hydrogen is 2.1. So 3.0 and 2.1. Okay, sodium and chlorine. I don't think I have sodium in my chart, but they'll have it on there. So let's do sodium is 0.9. Chlorine is 3.0. Difference is 2.1. Oops, I didn't do the difference here. This is 0.9. Okay, iron chloride. Iron is 1.8. Chlorine is 3.0. Okay, That's 1.2. And carbon, hydrogen. Carbon was 2.5. Hydrogen was 2.1. 0.4. Okay. What is the most polar bond we have there? Which one of those 5?
NaCl.
Perfect. NaCl. This is the most polar. It's got the highest number. Okay. So less than 0.5 is covalent. Greater than 2 is ionic. In between is polar. So is this bond here, carbon oxygen, polar, covalent, or ionic?
Polar.
Polar. Perfect. Very good. Okay, nitrogen hydrogen bond, polar, ionic, or covalent?
Polar.
Polar. NaCl, polar, ionic, or covalent?
Ionic.
Ionic. Iron chloride, polar, ionic, or covalent?
Ionic.
No, ionic is greater than 2. Remember, ionic is greater than 2. Covalent is less than 0.5. Between 0.5 and 2 is
Polar.
Polar. Just polar. Perfect. And carbon hydrogen bond is
Covalent.
covalent. It's less than 0.5. Perfect. You got it. That's polarity. Now, those are polar bonds. Okay? And now we've got what's called polar molecules or non-polar molecules. All right? So if we look at, so that's bonds are pretty straightforward. Now, when we put them into a molecule, it can change. Okay? We can have polar bonds, but a non-polar molecule because things can cancel out. Vector forces can cancel. If you look at, let's do a couple examples here. Let me think for a second. Let's do NH4, H2O, another one, and carbon tetrachloride. Okay, let's change that to NH3. I don't want to get an ion in here. Okay, that one. All right, let's start with carbon tetrachloride. You have carbon with 4 bonds. That's our Lewis structure. Now carbon, what's the number for carbon? For, let me chart back up. Electronegativity, carbon is 2.5. So you got a carbon chlorine bond. Carbon is 2.5, chlorine is 3.0. Yeah, 3.0. And that comes out to 0.5. Okay, that's a polar bond. Chlorine is more electronegative than carbon, so the bonds get pulled this way. So a carbon chlorine bond is a polar bond. Now, this is a polar bond. Now look at the molecule. The molecule has 4 of the exact same things attached to it. Okay? If your atom, in the central atom, has 4 of the exact same things to attach to it, they're going to cancel each other's out. It's like a tug of war. If you have 2 forces pulling exactly the same, it's going to cancel itself out, right? One's going one, they're called force vectors in physics. If one goes one way, one goes the other, if they're the exact same, in equal directions, they neutralize each other. So carbon tetrachloride has 4 of the exact same things attached to it. Okay? So this is a non-polar molecule. It's made up of polar bonds, but it is a non-polar molecule because everything cancels. Let's look at water. Hydrogen-oxygen bond. Oxygen is 3.5. Hydrogen is 2.1. It's a difference of 1.4. Okay. So this is a polar bond. Oxygen is more electronegative than hydrogen, so it pulls the electrons that way. Okay. Whoops, what did I hit? Okay, polar bond. It pulls electrons towards the oxygen. Okay. Now, look at the molecule. Is it a polar molecule or non-polar molecule? Are there 4 of the exact same things attached to that oxygen?
No.
No, there's not. There's a hydrogen. There's a hydrogen. Those are the same. And there's an electron, non-bielectron pair. Non-bielectron pair. Those are not the same. So this is a polar molecule because the force vectors do not cancel out. Because they're not exact. They have to be exactly the same. So if I had NH2NH3, nitrogen. Again, nitrogen, hydrogen is a polar bond. Nitrogen is 3.0. Hydrogen is 2.1. That's 0.9. So the NH bond is polar. There's more of it going towards the nitrogen. Okay? So you have a polar bond. Is the molecule polar? Okay. Does this have 4 of the exact same things attached to it?
No.
No. It's got a hydrogen, hydrogen, then it's got a non-bielectron pair. So this is a polar molecule. Okay. Let's do carbon, hydrogen, 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 fluorine. Right? Those are polar bonds. Is that a polar or non-polar molecule? Why did I put an L here? I should just,
Would it be a non-polar molecule?
does it have, to be non-polar, every force has to cancel out. Does it have 4 of the exact same things attached to it?
No.
No. So they're not going to cancel out. That has to be polar. Okay. If we did, let's do a couple examples here. If I had polar or non-polar?
Polar.
Polar. Carbon, fluorine, 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 fluorine. Polar or non-polar?
Polar.
Polar. Perfect. Carbon, let's do fluorine, 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 fluorine. Polar or non-polar?
Non-polar.
Non-polar. Okay, because everything cancels out. Let's do carbon dioxide. Polar or non-polar?
Non-polar.
Non-polar. Okay, because everything cancels out. It has 4 of the exact same things attached. 2 bonds, bond, 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 and bond. Everything's exactly the same. Okay, so you can have polar bonds, but it can be a non-polar molecule if everything cancels. If everything cancels, the force vectors cancel, and you're left with a non-polar molecule. And those are called dipoles, and we did that. You have a net dipole, no net dipole, everything cancels, we did that. All right, let's do a couple of examples here, and then we are done with this chapter. Cool. All right, let me draw, question says, draw the Lewis structure and determine if the molecule is a net dipole, which means are they polar or non-polar. If it has no dipole, it's non-polar. It has a dipole, which means it charges, it is polar. So let's do 8. Let's do HCN. Let me just pick a couple here to do that. Okay, let's do HCN and silicone trifluoride. All right, so HCN, we did that for our Lewis structure. Lewis structure should be 1. Carbon has 4, nitrogen has 5. We got to count for 10 electrons. Carbon, nitrogen. 2, 4, 6, 8, 10, 12, 14. Too many. So hydrogen, carbon, nitrogen. Remember, you can't double bond to hydrogen because it's terminal. So 2, 4, 6, 8, 10, 12. So one more. Okay, there's your Lewis structure for hydrogen cyanide. Now, is that polar or non-polar? Does it have a net dipole?
Polar.
It's polar because there's not the exact same things attached to carbon. So this one is polar. It has a dipole. Will attract each other in solution. Silicone, trifluoride. Okay, silicone has 4, right? Fluorine has 7, 28, 32. Okay, how many dots? We have 6 times 4, 24, 26, 28, 30, 32. That's our Lewis structure. Polar or non-polar?
Non-polar.
No.
Non-polar. 4 of the exact same things attached, they cancel out. Perfect. All right. And I think that's it. That's the end of chapter 9. Right? Yep, somebody, okay. Perfect. So now let's answer some of the questions from my emails. We'll do that, and then we'll answer those. And all that's good, all that's good. All right, let's do a couple of questions here. It says, conversions. Well, any questions on chapter 9 so far, what we covered?
Nope.
All
No.
right. That was a good chapter, huh?
Yeah, I like the later chapters. I've done most of them already. I don't like chapter 7. It's the only one I don't like.
I
Yeah,
thought chapter 8 was really hard.
yeah. There's some hard concepts. All right. This one says convert 18.0 kilojoules to calories. Okay, so write down what we're starting with, 18.00 kilojoules. And let me see what my conversion, I have my conversion charts here. Oh, it's beyond this. It'd be right up here on this. Let's see if I have calories and kilojoules. No, I'll have to look that one up. No calorie ones. All right, what's the conversion number? And let's convert this into joules. So kilojoules is 1,000 joules, and joules to calories. You just look up what that is. I think I had a chat comment here too. Look up anything. Okay, perfect. Dun, dun, dun. Let's go to the chart up here. I want joules to calories, right? I want to go to calories. And try to find the numbers here. All right, so 1 joule, again, I'll give the numbers that you need. 1.00 joules is equal to 0.00, how many zeros are there? 1, 2, 3, 239, 006 calories. So 1 joule is equal to 0.000239006 calories. So kilojoules have canceled, joules have canceled, and you're left with calories. So you put in your trusty phone calculator. 18 times 0.000239,006 equals that. And you times by 1,000. So it's equal to 0.000239,006. 0.004302 times 10 to the third. Okay, so 1, 2, 3. Comes out to 4.302 calories.
I'm sorry, when it says 0.
Okay.
Is that a 0 right there?
Converted kilojoules to joules, and then joules into calories. These are conversion numbers. 1 joule, the same thing as 0.000239006 calories. Kilojoule is 1,000 joules, 10 to the third, and they started with 4 standard digits, and you have 4 standard digits in your answer.
That's because I'm trying to read the last
Okay, so
second to last set of numbers.
So I get 4.302. Next one is 100, and that one was right. So we go to the next question here. And it says use the scale for the specific heat of gold. It's missing some of the information though. I need to know the weight. All right, so I think Stephanie sent this in if I remember right. Do you remember the rest of the question? It's missing some of the information. It says use the want to calculate the specific heat of gold. They want the specific heat of gold. Okay. And it doesn't give you any information. To get the specific heat, they put it looks like it got cut off somewhere.
Can I share my screen?
We'll come back to that one if we still have it. Okay, here's more of a problem. It says the chemist heats a block of gold as shown in the interactive, then places the metal in a cup of oil at 25 degrees centigrade instead of a cup of water. The temperature of oil increases 26. Okay, calculate the mass of oil in the cup. Use specific heat of gold and specific heat of oil. Okay, so what we basically have is, for this question, you've got your cup, and it's filled with oil, not water this time. It's filled with oil. The specific heat of the oil is equal to 1.74 joules per gram degree centigrade. Okay, you're heating the block of gold. The cup oil is originally at 25 degrees centigrade. So the oil starts at 25 degrees centigrade. It increases to 26.26 when you put the gold in it, degrees centigrade. Specific heat equals we're missing information here though. This is part of a lab, it looks like, and it's some of the stuff you have to do to get the weight of it. So let's see, so we have this Q equals specific heat mass delta T. Okay, did you get the mass of the oil? I think this, Stephanie sent this one in, but you need the calculate the mass of the oil in the cup.
Can you hear me?
It's missing. Did you have to weigh the oil in the lab? It's missing some of the information.
I don't think you can hear us. We can hear him. I could hear the rest of you.
Okay, you hear me? Okay, good, cool. Okay, so it says to add water to the cup. Add water to the cup. It's missing some information here. You have to either have either the heat generated, it gives you that, but I'm missing, I have to have one of those two variables. What am I missing here? No, it doesn't tell you what the gold is shoot out to either. It's got to be in the lab. We have to measure the oil on the balance or something, because there's not enough to solve that problem. Let me see if this one will work. Chemist heats 32.85 of lead to that much temperature, then places in a cup of water. The final temperature of the water. Specific heat of lead is that. Okay, so you have the specific heat.
Can you guys hear me?
Yeah, I can hear you now.
Okay.
Can you hear me now? Because I was asking a lot of questions and
Oh no, now I can hear you. We're coming through before.
Asking questions, but you couldn't hear us.
Oh, something must have been turned off on my end. Okay. These lab ones are hard for me to, because I'm not, you have to get the,
Yeah, I was asking if I can share my screen with you guys.
sure.
Okay. I think you have to make me a co-host in order to share it.
I gotta stop sharing mine, then how would I do it? Do I stop sharing my screen?
Yeah.
Okay.
Yeah, I think so.
We'll try it. Okay. Now what?
Okay, now I'm gonna share my screen.
Okay.
Okay. Can you guys see it?
Yep.
yeah.
Okay. So this is the question that let's go to this one. I was struggling with this one.
Okay.
So do I have to get the, what do I have to do first? Because honestly, I don't even know.
You have to add water to the cup.
I have to do it.
Oh, wait. You have to measure the cup first, without the water first. Okay. So measure the cup. It's 4.00 grams, right?
Yeah.
Okay. Now, so take the cup off, fill it with water.
It's
and measure
64.
64. Okay, so you have 60 grams of water, right?
Right.
Okay, so take the temperature of that. It's 25 degrees centigrade. Okay, so we know the water. Now take the thermometer away. Now we're going to heat the gold. Okay, take its temperature. 65.17. Okay. Now take the gold, dump it in the water. Oh, wait a minute. We gotta get the mass of it first. Sorry.
It's okay.
Before, well, you don't have to heat, yeah. Mass of the gold is 38.600 grams. Okay, now heat the gold. Or you already heated it?
Yeah.
Okay, fill the water. Hope the numbers don't change. Put the gold in there. Now take the temperature of the water. 25.
0.78.
Okay. So we got all our values. Okay, so I've got, put it down so I can make sure I got everything. Specific heat, M delta T. It wants to know what's the specific heat of gold. Okay. We know the water, we know that. So we got our specific heat, we got our mass, and we got delta T for the water. Then we want to calculate this, we want to calculate the specific heat of gold. Specific heat equals our Q value, which we're going to calculate, divided by mass of gold, which mass delta T. All right. Give me my screen back and we'll.
Yes.
All right, perfect. Actually, that worked pretty good. Get my screen. Here we go. All right, so let's clear this. The first thing we did was we got our mass of water. So H2O, mass is equal to 60 grams, right?
Yeah.
The 3 zeros after it. 60 grams of water. Okay. Then we took it at, water went from 25 degrees centigrade to 25.78. That's all it did. 25.78. Okay. So the change in temperature was 0.78. Okay. And so there's your mass, there's your change in temperature, and we know the specific heat. So the Q value for water, because remember, the heat transferred from the water to the metal, it's the same as a metal to the water. So the Q value for our water is going to equal our specific heat of water, mass delta T. Specific heat of water is 4.184 joules per gram degree centigrade. The mass of the water we found was 60.000 grams. And the change in temperature we said was 0.78 degrees centigrade. Okay, so centigrade cancel, grams cancel, we're left with joules. So the Q value for water is going to be 4.184. You want to calculate out here? Okay, 4.184 times 60 times 0.78, which is 195. And where are we at? We had how many significant digits? Well, with the water of that, but 195.8. Okay, and that gives us joules. Okay, so far so good?
Yeah.
Okay, that's the Q water. Now, the Q of the water is the same as the Q of the gold. So we're looking for the specific heat of gold. So specific heat equals Q divided by mass delta T. Just rearrange this equation right here. Our Q value is 195. Gosh, I can't draw with this thing. 195.8 joules. The mass of the gold was, what was the mass of the gold? I thought I wrote it down. Oh, 38.600. Mass of the gold is 38.600 grams. And the change in temperature for the gold we heated up to, what we heat the gold up to? 65.17? Yeah. We heated the gold to 65.17, and the temperature, final temperature is 25.78. Okay. So let's do our temperature first. Let's say 65.17 minus 25.78 25.78 gives you a temperature 39.39. So we take 195.8 divide by 38.6 divide by 39.39. So 195.8 divided by 38.6 divided by 39.39, sorry, equals 0.1288. If we're going to get to 3 to 4 significant digits, 0.1288, yeah. So we should have a specific heat of gold is 0.1288 joules per gram degree centigrade.
Okay, thank you.
That makes sense?
Yeah, I actually forgot to do the second step.
Okay, that's probably why I didn't look right, huh?
Yeah.
Okay, and it looks like you missed a conversion on 600. Let's see, one more conversion here. I think that's the last question on that for that one. Let's do clear all. We're going to convert. You want to convert 6. I can't on the copy didn't show it blocked it off what it wanted to convert into. It has 634
2 meters.
megameters and it wants to convert to what?
Meters?
To meters, right?
Right.
Okay, so 634, right now what you're starting with, megameters, and then megameters go on the bottom, meters go on top, and mega is 10 to the 6, right? So it's equal to 634 times 10 to the 6 meters. And scientific notation is 6.34. I don't know if they want a scientific notation or not. Or they want it, how do they want it written out? Oh, units to meters, okay. 6.34 times 10 to the, where are we at? I mean, this number is smaller, make this number bigger by 2. 6.34 times 10 to the 8 meters. Or if they don't want a scientific notation, all you do is sort of 6, 3, 4, and then 6 zeros, right? Yeah. Thousand. 634 million. It depends how they want it written out. I don't know how they want it written out.
Okay. Thank you.
That makes sense?
Yeah, it does.
Okay. And then we have some questions for my testing. Let's get those pulled up. We'll go through those here too. Oops, wrong button. So there we are. All right. Okay, it says addition. All right, let me get these cleaned up. And question says the addition of aqueous sodium iodide to a solution of aqueous silver nitrate. So sodium iodide, we're gonna start with sodium iodide, NaI. Okay, and aqueous silver nitrate, AgNO3. And it wants to write the balanced molecular equation for the reaction, including the phases. Okay, so it tells you these are aqueous, right? It tells you right in the equation these are aqueous. It says aqueous solutions. Okay, what is it going to form? It's going to form double displacement, so silver iodine plus sodium nitrate. And we look on this, now we got to determine if those two are going to be soluble or insoluble. So go to the solubility table, AgIN3. So silver nitrate no, it's not silver nitrate. It was silver iodide, right? Silver iodide. Where's silver iodide? There's iodide. Silver iodide and sodium nitrate. Sodium nitrate. Okay, so nitrate, look at it, is going to be aqueous. Silver iodide is going to be solid. Okay, so this is going to be solid and this is going to be aqueous. Now, is it balanced? Yes, no, maybe.
Yes.
Yep, it's balanced. There it is. That's the answer. Okay. Now we're going to do more of that. Okay. Now what you'll see on the midterm, you'll see to balance that, and then you'll see to have the total ionic equation and the net ionic equation. So the total ionic equation means you're going to break it up into ions where you can. So Na plus plus I minus plus Ag plus NO3 minus. Okay. AgI does not break into ions because it's a precipitate, it's a solid. Plus Na plus NO3 minus. Okay. This is your total ionic equation. This is your molecular balanced equation. And now you want your net ionic equation. Net ionic equation means we remove the spectator ions. So we got Na plus, we got Na plus, NO3 minus, NO3 minus. So we've got our net equation as I minus plus Ag plus goes to AgI, solid. And those two other equations. That's the net ionic equation. You got to write those three for your midterm. The molecular, the total, and the net. And be able to identify spectator ions. All right. Any questions with that?
No.
Okay. Then the other one says, perfect. Write balanced chemical equations reaction of copper with sulfur. Include phase symbols. Let's see if I can blow this off and see a little bit better. Okay, and you'd have to look up, you're gonna have copper 1, which is a solid, plus sulfur, which is a solid, goes to Cu2 sulfur, solid. Okay. What's wrong with that equation?
It's not balanced.
Unbalanced, perfect. How do we balance it?
Add a 2 on the left side in front of the Cu, in front of copper.
There you go. That's the correct answer. Perfect. Okay. I'm trying to put those, I can't see them real clear. It says the reaction, says the reaction of strontium with oxygen is similar to the reaction of magnesium with oxygen. Write the balanced chemical equation for the reaction of strontium with oxygen. Okay. Let's pull on the periodic table so I can see what we're looking at. And strontium, okay, magnesium reacts the same. So it's going to be strontium with a 2+ charge, and it's going to react with oxygen with the 2- charge. So it wants to write the including phase symbols. So let's put back here. Okay. They want strontium plus oxygen. Strontium is a solid, it's a metal. Oxygen is a gas. And it's going to go to strontium oxide, SRO, which is a solid. Okay. Because strontium is +2, oxygen is -2. Connects 1 to 1. Okay. So now all we can do is balance the equation. Is it balanced?
No.
No. There's 1 strontium, 1 strontium. That's good. 2 oxygen left. Yeah. I keep moving my thing. 2 oxygen on the right. So put a 2 here. And I need to put a 2 somewhere else, right? Right in front of here. 2 strontiums, 2 oxygens, 2 strontiums, 2 oxygens. And we're balanced. Strontium is a solid. O2 is a gas. And strontium oxide is a solid. That's a G. I know it's kind of hard to see, but that's a G.
Wait, so next to the O2, that's a G right there? It's not an S?
Right. No, it's a G. Oxygen's a gas. So it'd be 2, and my writing is terrible. With metal, solid, plus O2, gas. Oxygen's a gas, goes to 2, SRO, solid. There. Is that better?
Yeah, thank you. Sometimes it's
No.
hard to read it.
No, my writing's terrible. Terrible. Okay. This next one says determine whether each reactant gains or loses electrons to form an ionic compound. Okay, and your examples are magnesium plus sulfur goes to MgS, and your other one is iron plus iodine goes to Fe, iron iodide. Okay, and you want to know if this gains or loses electrons, and this gains or loses electrons. Okay, so Mg, okay, is that going to lose electrons or gain electrons? Look at the periodic table. Look where it is. Okay, let's look at the periodic table. Magnesium, and what was it was combining with? Sulfur. Sulfur. Okay. Remember this line here? To the left are metals, to the right are nonmetals. Okay. Metals give up electrons, they have a positive charge. Nonmetals accept electrons. So magnesium is going to give up electrons because it's Mg plus 2, right? So it can get 8 in its core. Sulfur is going to accept 2 electrons. So it can go to be like argon. Everything wants to have 8. Metals give up electrons, nonmetals accept electrons. So magnesium is going to, what did the question say? Gain or lose? I'm trying to remember the wording of it.
Yeah.
Okay, gain or lose. So magnesium is going to lose electrons. Sulfur is going to gain electrons. Iron is a metal. It's going to lose electrons. Iodine is the nonmetal. It's going to gain electrons. Does that make sense now?
Yeah, thank you.
Oh, no problem. Metals always lose, nonmetals always gain. And there's one more on this one. The reaction. Okay, let's write this down so you can see it. The reaction of lithium with bromide. Lithium plus bromine, okay, is similar to that of sodium with bromine. Write the balanced chemical equation for the reaction of lithium with bromine. Include phases. So lithium is a metal. Bromine is usually bromine can be a gas or this would probably be liquid, is what I would say. But it could be a gas also, depending on where you're at, what temperature you're at, what pressure.
Is that an S near the lithium? I'm sorry.
My S, solid. We can check real quick. Phase of bromine at room temperature. I assume they're room temperature. Yeah, bromine is a liquid because electron property. Okay, at room temperature, bromine is a liquid but converts to a gas very easily. So I think they want the liquid form of it. They didn't specify in the question, but that's what I would say. I had to look that up. Okay, so lithium plus Br2 goes to LiBr, lithium bromine. Okay, so I said write the balanced equation, and this is a lithium bromine is a solid. So you put 2 in front of here, 2 in front of here. Again, that's not a good question because bromine could be Br2 or Br. It could be a gas or it could be the liquid phase.
Yeah, a lot of the questions on the homework, they're not very direct, so it makes it kind of hard for us.
Yeah. Okay, but there's your balanced equation.
So it's 2 lithium and then bromine 2. Is that an L right there in the parentheses? I'm sorry.
That's an L for liquid.
Okay.
They should have specified that in the problem, but I'd say it's a liquid room temperature, but it evaporates really quickly into a gas. So I would keep it as a liquid. All right. Did I get the question everybody sent now? I think I covered everything I got sent to me. Any additional questions? Anything else?
Yeah, are you gonna curve the test? Just out of curiosity.
Definitely.
Woo! Needed that.
No, I mean, I try to make it fair to everybody, but I think differently than other people sometimes. And, you know, if everybody misses something, people shouldn't be punished for it. That's how I look at it. So everything's going to be curved.
Yeah, because I was about to say, can we curve the homework too? Because the wording's terrible.
Yeah, everything will be curved. Yep. But your grade at the end of the semester will be curved. So everything's curved towards the whole class.
Hallelujah. Praise the Lord.
All right, so we'll do that. And midterm is Monday, huh? So there's.
Oh, I thought it was tomorrow. My bad.
It was on Saturday.
Isn't it Monday?
I thought it was on Saturday.
Yeah, tomorrow. Isn't it? Yeah, because tomorrow's the 9th.
Oh, is it? Oh, that's right. It's tomorrow. God, I'm trying to. I think it was Monday. Tomorrow's the 9th, right?
Yeah.
Yeah.
Unfortunately.
Yeah. Oh, so we do have class on Monday then. Okay.
The midterm is all online, right? There's no like writing other than you doing the figuring out the problems.
You got to give me an essay. No, I'm just kidding. I don't. It's all online, all multiple choice. There'll be 2 extra credit questions at the end, which is just kind of fun questions. You guys write those in. They're very simple answers though. Yeah, that's the only writing you have to do. Yeah, they're not related to chemistry. They just something you can look at and kind of figure out. You got some extra time. Sure, the test is tomorrow. Yeah, I got to check all that. All right. Any other questions?
No, that is all. Thank you.
All right, you're welcome. I'm trying to think. Yeah, it'll be open for 24 hours, and take your time and do the best you can with it. Okay.
Okay.
Any questions? Meantime, I'll check my emails in the morning too. So you have something your question with tonight, let me know, and I'll be up in the morning and I will answer them. Okay.
It looks like Tara's got a question.
Who does? Oh, is it in chat?
Yeah, it's in chat.
It's not popping up on my thing here in chat. Hold on. I had trouble with this doing it last time. All right. You can't hear us. The Lewis structures. It says the Lewis. Okay, I can see chat now. I don't think you can hear. Yeah, I guess there was a time when I couldn't hear everybody. Something got turned off. Okay, so I can hear you now. Yeah, Tara said the Lewis structure in chapter 9. I don't know what the question is. Go ahead and type it into chat and I can see it now. If anybody has a question. Oh, you emailed it. Okay, let me close chat again. Go to my emails. We'll pick that up. And cut this off. We did that one. The only email I got. Did we do that one? Or did I not do that one? Let me check chat again, see if I can open this up.
Looks like she typed her question in.
Yeah, because I didn't get that on my email. It didn't come through for some reason. A Lewis structure for the carbonate ion CO3. It's It's CO3 2 minus. That was got switch. That's okay. It's shown but incomplete. Complete the structure by adding the formal charges and the non-bonding electrons. Then draw the other 2 minus. Okay, perfect. Good question. All right, so let's go. And we should also still see. I can keep that up and do this, right? Okay. So I can still keep that up and you'll see that. Okay. So the Lewis structure is carbonate ion CO3 2 minus. It says the Lewis structure is incomplete. Okay, so put the Lewis structure here. CO3. And I'm not sure, I don't have the, it's shown, but incomplete. Complete the structure by adding the formal charges. All right, so let's do this. Before I do that, okay, carbon is how many? Carbon is 4. Oxygen is how many valence electrons? We didn't forget already, right?
6.
6, perfect. 6 times 3 is 18. And then we got 2 for the negative 2 charge. So we got 14, we got 24. We got to count for 24 valence electrons. So carbon goes in the center, then oxygen, then oxygen, then oxygen. And then we make it all have 8. Okay. Count the electrons. There's 6, 12, 18, 20, 22, 24, 26. So too many. So we got to add a double bond. And we'll put our electrons in. I think that's what they want. Two minus. Okay, that's the complete one. That adds the complete the structure. And then we got to add the formal charges and the non-bonding electrons. So there's the non-bonding electrons are added. There's 24. And then the charges. So let's put the formal charges. So on this oxygen, on this oxygen, on this carbon, and on this oxygen. Let's do formal charges. So on the way to the left, the oxygen on the left has the normally 6, that's its neutral valence electrons from the periodic table, has 6 valence electrons. So minus 4 for the dots, then minus 2 for the bonds. 6 minus 4 minus 2 is 0. Formal charge is 0 on that one. The top oxygen, normally 6, and it's 2, 4, 6. 6 minus 1 is negative 1. There's your formal charge on that oxygen. Carbon is normally 4, and there's 4 bonds. 4 minus 4 is 0. Oxygen, again, 6 minus 1 for the 1 bond is negative 1. There's 2 negative 1s from that accounts for this negative 2 charge when you add the formal charges up. So now you got your formal charges and you've got your correct structure. Now it says draw the other 2 resonance structures. Remember the resonance structure, we just move the double bond. So you would draw, okay, we usually put an arrow between showing that a double arrow because it converts to both of them. Oxygen, carbon, double bond, and a bond. Okay. We'll fill these all in. Let's put these boxes a little closer. Don't get confused. Okay, those are your other 2 resonance structures. Now remember, those don't, in reality, it's a hybrid. So in reality, it's really oxygen, carbon, oxygen, carbon. And this is 1 1/3, this is 1 1/3, this is 1 1/3. Everything's spread out evenly. It's called a hybrid in reality, but it gives you a very stable structure. Okay, even though you got 2 formal charges on it, it's structured because of the resonance structure that can be formed. It allows electrons to spread out and become very stable. Is that what is it? Was that did that did that answer your question, Tara? I think so. Okay. Was there another part of it that didn't get answered? See if anything. Was there any question on the resonance structures like that or the formal charges? Those are new concepts. Okay, draw a Lewis structure for SO2, which all atoms obey the octet rule. Okay, so let's do SO2. Let's go down here and we'll do SO2. Okay, we'll do the same thing. Sulfur is what? Sulfur has how many valence electrons? Sulfur has, did I cut everybody off again? Can anybody hear me?
Yeah, we can hear you.
Oh, okay, you guys. I wonder if I hit something. I don't know what I hit last time to cut that off. All right, so how many does S have? How many valence electrons?
Would it be 6?
Would be 6. Perfect. Oxygen has
6.
6, and there's 2 of those, so I need 18. Sulfur goes in the center. Oxygen, oxygen. Okay, and let's put our dots to give everything 8 and count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's too many. So we need to make multiple bond. So oxygen, double bonded sulfur, bonded oxygen. Okay. And we have 4 there, 2 there, 6 there. 2, 4, 6, 8, 10. Whoops, I'm missing one. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. And it could be represented by, we can put the bond on the other side. That's a resonance structure. Okay. Those are 2 resonance structures. So draw a Lewis structure SO2 in which all atoms obey the octet rule. Show formal charges. Okay, so your formal charges are going to be oxygen, sulfur, and oxygen. Oxygen is normally 6, minus 4, minus 2 is going to be 0. Sulfur is going to be usually 6, minus 2 is 4, minus 3 is going to be plus 1. And oxygen is going to be 6, minus 6, minus another one is minus 1. Okay, that's the first part. Okay, formal charges, and it shows the resonance structure. The second half, draw a Lewis structure for SO2 in which all atoms have a formal charge of 0. Okay, 6, all atoms have a formal charge of 0. You would draw L, S, oh, I'll take straight at least. Whoops, sorry, -1. So oxygen, sulfur, oxygen, double bond, sulfur 6. Okay. In that compound, everything has a formal charge of 0. Now it breaks the octet rule, but sulfur can do that. That's one of the extents it can do. Okay. It's in the second row below that. So if we do the formal charge here, we got 6 minus, wait, no, I did something wrong here. I didn't put my dots right. Hold on. I didn't make my dots right. My fault. I put 2, 2, 2, that's a 0. There we go. Much better. 2 dots there. Okay, so this oxygen has 6 minus 4 minus 2 is 0. Sulfur has 6 minus 4 minus 2 is 0. Oxygen has 6 minus 4 minus 2 is 0. So there's a Lewis structure which all oxygens have a formal charge of 0. So this one on the top shows your octet rule. And this one down here shows the one that all the formal charges are 0. Does that make sense? Did that answer it? The question was, right. This part, they don't usually ask something like this where you want to get all 0 formal charges. It was just to show if you could make formal charges. Yeah, it wasn't very clear, but that's what they were asking. Does that make more sense now? Perfect. Good. All right. Good. Any other questions? Like I said, if you have questions tonight, email me. I'll be glad to answer them first thing in the morning too when I get up. Oh, fluorine. We have another. Fluorine is the most electronegative element. In a bond between fluorine and any other element, fluorine has a partial negative charge. Yes, because what it's going to do is fluorine is going to be the most electronegative. So fluorine is 4. Nothing else has an electronegative 4. So anything else, like say with oxygen, oxygen was a charge of 3. So the difference is 1.0. So your electrons are going to always be drawn towards fluorine. Any compound that has fluorine in it, okay, is going to be a polar bond. Not necessarily a polar molecule, but a polar bond. Because fluorine is the most electronegative element in the periodic table. Every element is below that. Okay. Direction of the polarity of each of the covalent bonds. Fluorine, oxygen. Like you said, fluorine is 4, oxygen is 3. They want a delta minus, delta plus. Okay. Delta just means small. Delta in Greek, large delta means that's a big change. Small delta, which is this figure right here, that's a lowercase delta, means a little change. Because they're only pulling electrons. It's not making a whole charge. But there's going to be a partial charge. You could draw it with an arrow, or you could draw little delta signs. There's 2 ways to do it. Delta minus and delta plus, or just draw an arrow with the end pointing to it. Okay, so that'd be the delta notation way that way.